Welcome. We are looking at phase field modeling. We looked at the spinodal decomposition modeling and we saw in 2 dimensions how it happens. Now we want to look at order disorder transformation. Just to remind ourselves of the steps that is involved in building a phase field model, I am going to use the same way like I did in the spinodal decomposition part. Let us go step by step. Step 1 is to describe the microstructure using an order parameter. In the case of a system which undergoes order disorder transformation, so what I am looking at is like this. So, I am looking at a microstructure and I am going to say that there are regions where you will have the one type of ordered domain where the central point is occupied by say one type of atom, and so let us say those are these domains. And the other parts are basically going to be one where you have the other ordered domain where the body the cube corners are occupied by the one type of atom. So, the other type of atom was at cube corners here, the other type of atom is now at the body center here. So, these are the 2 domains. So, let us call this as 1 and this as 2. So, basically we have is 1 2 1 maybe something like this. So, this is all 2 and this is 1, and so there is some region 2 here and region this is 1, and so this is 2 and so on. So, we are describing the microstructure using an order parameter. Let me call that as order parameter as phi, and if it takes a value of 1 that corresponds to one of them, if it takes a value of 0 that corresponds to other, and in the region where it goes from 1 to 2, phi goes from phi equal to 1 to phi equal to 0. So, the step 1 order parameter is phi, and phi is a non conserved order parameter. Okay. Non conserved order parameter, and what does it represent? It represents the type of domain structure, whether in the domain the A atoms are at the body center or at the cube corner, for example, is what this represents. So, that is the step 1. Step 2 is to write the free energy functional. So, we are going to write the free energy functional as nothing but f0 of phi plus kappa del phi whole square dV. So, this is the free energy functional. So, every phase field model starts with the identification of the order parameter and writing the thermodynamic functional. It could be free energy, it could be entropy in terms of the identified order parameter. Of course, step 3, because now what we are dealing with, d by dt of integral phi dt is not equal to 0. So, it is a non conserved order parameter. So, in this case then the equation that we write is different, that is the Allen-Kohn equation or Kohn-Allen equation. This equation says that dou phi by dou t is equal to minus L mu, where mu is that is minus L del f by n v by del phi or del g by n v, whatever we called it. Okay. So, now what is del g by del phi, which is the chemical potential, dou f0 by dou phi, let me again call it as some g of phi minus 2 kappa del squared phi. So, at the end of step 3, so this is the Allen-Kohn equation, which basically tells what is the kinetics. Okay. So, basically this describes kinetics, like in step 2 we described the thermodynamics, in step 3 basically we are describing the kinetics, either that is a Kohn-Hilliard equation or Allen-Kohn equation. So, it says that rate of change of the order parameter is given by this. So, it is 2 kappa L del squared phi minus L g of phi. So, this is the equation we need to solve. Now, step 4 is of course to solve this equation numerically. Again we are going to use a semi implicit Fourier spectral technique. So, how does that work? So, phi tilde t plus delta t minus phi tilde t by delta t is equal to minus 2 kappa k squared L phi tilde at time t plus delta t minus L delta t g tilde at time t. So, that implies phi tilde t plus delta t is equal to phi tilde t minus L delta t g tilde t divided by so this also delta t. So, delta t is not here 1 plus 2 kappa k squared L. So, this is what we want to evolve, and as usual we are going to write and remember this k squared is now k x squared plus k y squared, because we are trying to solve it in 2D. Okay. Previously it was just in 1D, now we are trying to solve it in 2D. So, this is what we want to implement in the code, and we want to look at how the microstructure looks like. So, this describes how the domain structure during order disorder transformation is going to evolve. That is what this equation is describing, and that is what we are going to look at. So, let us go write the code as usual. We will say 2D Alencon FFT dot OCT. That is what I will call. So, as usual clear all CLC, CLF and then more off. So, we are going to do this, and then I am going to define kappa to be equal to 1, A to be equal to 1. A is the parameter in the bulk free energy density F0, and I am going to call L also to be equal to 1. So, we have defined all these parameters. So, let us take Nx to be 128 for example, Ny is equal to 128 for example. So, we have defined the domain size, and we want to describe phi. So, for I is equal to 1 to Nx, for j is equal to 1 to Ny. So, phi of I comma j. So, I am going to start with the same kind of initial profile 0.5 plus 0.1 times 0.5 minus rand. So, this will generate a random number between here between 0 and 1. So, when it is subtracted from 0.5 it will give a number between minus 0.5 plus 0.5. So, the noise strength will be of 0.1. So, it will be 0.5 plus or minus 0.05. So, that is what this is going to be. So, as usual we are going to plot mesh phi, and we are going to look at the projection from the top, and I am going to put a pos 0. Okay. Now, we want to evolve. So, we are going to again for m is equal to 1 to 10 and for. So, we are going to plot 10 times. So, the inner time loop n is equal to 1 to 10 for example, right, and end for. Okay. So, within this loop what are we going to do? We are going to say for I is equal to 1 to Nx, for j is equal to 1 to Ny, and for and end for. So, for periodic boundary condition implementation we need the other things. So, we need the time step. Let us take time step to be 0.1 for example, or 0.5 for example, and we want to define half Nx to be Nx by 2, half Ny to be Ny by 2. So, these are the for implementing periodic boundary condition. We also want to define del k x to be 2 into pi by Nx, and del k y to be equal to 2 into pi by n y. Okay. So, these are the interval in the reciprocal space in k vector when we are doing. Okay. So, let us now define, we want to define G, which is nothing but 2 into A into A dot star into phi dot star 1 dot minus phi dot star 1 dot minus 2 dot star phi. So, that is 2 A phi into 1 minus phi into 1 minus 2 phi, because we have assumed that f 0 of phi as A c squared into 1 minus c whole squared. So, that is why it is like that. So, after we get that, so we take a g hat to be equal to, so this should be outside. Okay. So, first we do this and then we go into the and we take g hat is nothing but FFT2 of g and then c hat to be FFT2 of c, sorry, phi, this is phi hat, right. So, this is the phi is the order parameter and that is what we are doing. Now, we go in and we say c hat. So, before that we need to implement the periodic boundary condition. So, if I minus 1 is less than or equal to half n x, then I am going to say k x is equal to I minus 1 into del k x, and if and then I am going to so if I minus 1 is greater than half n x, then I am going to minus n x del k x. Okay. So, same thing we are going to implement for y. So, for j minus 1 and j minus 1 and this should be y, this should be y, then we are going to say k y and this is j minus 1 and this is j minus 1, this is going to be 1 y, this is y, this is y. Okay. So, now we can calculate k squared as k x into k x plus k y into k y. So, now we are ready to say c hat sorry phi hat I comma j is nothing but phi hat I comma j minus L into dt into g hat of I comma j and then divided by 1 plus 2 into kappa into L into dt, right, 2 into kappa L dt and k square into k square. So, at the end of it, so we have evolved the order parameter and we come out and then we take the inverse Fourier transform, phi is equal to real of inverse first Fourier transform of in 2D of phi hat. So, this we do and that is the phi, and so once we get the phi we plot it. So, this is the time loop and this is the 2 for loops and this is the time loop. So, after n time steps, so we want to plot it here. So, mesh phi and view 2 and pause 0. Okay. So, just to make sure that let us give this pause slightly longer, so that before we actually come to the microstructure we will be able to see. Okay. So, let us now run source 2D Alencon FFT. Okay. So, as you can see, initially everything was noisy, and then you suddenly start getting the red and blue regions, which corresponds to domain 1 and domain 2. And as you can see, the evolution is very, very fast. That is because Alencon equation is a non-local equation. Unlike diffusion, there is no continuity that you have to see. Okay, things evolve very fast, and after that the microstructure actually coarses. Okay. So, this is the coarsening regime that we have entered. So, the interfacial energy minimum will be when this one of the phases is circular and is embedded in the other phase, and that is what is happening. And you can also see the periodic boundary condition. This is basically a continuation of this, and this is basically a continuation of this, and this is basically a continuation of this. So, even though it looks like 4 particles, actually there is only one particle that is consistent with the periodic boundary condition if you look at. Okay. So, that is what is evolving, and this has come out, and you can again go look at the microstructure a little bit more carefully, and this is what it looks like. Okay. So, you have this composition 1, the order parameter 1, and you have this order parameter 0 regions, and in between it goes from 0 to 1. Okay. So, that is what it is, and this is what we are seeing as projection. So, this is the Alencon equation implemented in 2D. So, to summarize, so we have looked at 2 important cases, phase separation and ordering. In phase separation, the spinodal decomposition, and in ordering, the system that undergoes order disorder transformation. So, we have seen both these cases, and we have seen how to implement, how to write the phase field equation in the first place, identify the order parameter, write the free energy functional in terms of order parameter and its gradients, and write down the kinetics, which is Cahn-Hilliard or Alencon, and of course, then implement it numerically. In 1D, we saw that we can even solve some of these equations analytically, and we looked at the analytical solution in one of the previous lectures. But now on, we are just going to stick to solving these equations numerically, primarily using semi-implicit spectral techniques. Okay. So, we will now take one by one cases of interest to a material scientist or metallurgist, and in each one of those cases, we will go through this process of identifying order parameters, writing the free energy functional, writing the evolution equation, and solving them. Okay. So, which is what will form the last section of this course. So, we will take at least some 3 or 4 scenarios like that, see 3 or 4 phenomena like that, and try to model them using the phase field model. Thank you.